Hello, biomechanists, and welcome to Biomechanics on Our Minds.
Welcome to Boom, where we have
Biomechanics on our minds.
Boom.
Boom, boom, boom.
Boom. I'm Hannah.
I'm Melissa, and we are grad students at Stanford, and here to talk about the exciting biomechanics going on in our world and in our minds.
And your world, too.
And your world. In the world around all of us. Okay. We have an exciting episode today. We did an interview with Jacque Cole, who studies the osteovascular system, and she's an assistant professor at the University of North Carolina and in NC State. Mm-hmm. Yes, so we will introduce her a little bit later and have a cool interview with her. But first, a bit of boom.
Bit of boom. Gucci. Bit of boom. Louis. Bit of boom. Bit of boom.
There was a research paper published recently in the Journal of Biomechanics by Li-Ming Xu et al. From Mechanical Engineering Department at the University of Tokyo in Tokyo, Japan. And it was titled A Subject-Specific Finite Element Musculoskeletal Framework for Mechanics Analysis of a Total Knee Replacement. And what they did was took an approach for evaluating total knee replacements by combining finite element analysis and musculoskeletal models. And I really like this because it combined modeling at different levels. So with the finite element model, you can look at things like stress and strain distribution across the joint or on the knee replacements, but then you have to make estimates of what boundary conditions to apply. So what are the joint loads that you should be applying to the finite element analysis of the knee? But then with musculoskeletal models, you can have a whole skeleton, but it consists of rigid body segments, so the bones connected by joints and muscle tendon units. And it's able to better consider the individual characteristics of the patients for biomechanical analysis and give you joint contact forces and other boundary conditions to then use in the FE model.
That's really cool. Like, you don't have to just pick one. You don't have to pick, like, the simpler, faster musculoskeletal model or just get the really high-resolution finite elements, but you can kind of have a nice hybrid of the two.
Yeah, exactly. So they combine a finite element of the prosthesis component and then CT scan-based subject-specific finite element bone model, and then they scaled the musculoskeletal model to create a subject-specific finite element musculoskeletal model with ligament constraints.
Mm. And so were these subjects, this was before and after knee surgery?
So it was basically used as a prediction tool. So they put motion capture markers on subjects, and then the marker locations were put into an inverse kinematic analysis to calculate the joint kinematics. And then joint kinematics and ground reaction forces were put into an inverse dynamics model. And then from there predicted the joint moments, muscle lengths, and muscle moment arms, and muscle velocities, and eventually predicted muscle force. And so then you had the inputs of the muscle tendon forces, ground reaction forces, and joint kinematics into the finite element musculoskeletal model, which then incorporated bones, implant ligaments, and muscles, and then has a capability of calculating the joint internal motion, joint contact forces, contact pressure, and the contact area and stresses. And basically they then fed that back into the inverse dynamics model until the contact force was in a particular threshold.
Cool. And then how does this help us if we have this model? Were they able to predict something that they weren't able to do before, or how are they?
Yeah, so I think that the novelty of this is the workflow for the combination of finite element and musculoskeletal
like now
models.
They did it, other people can do it.
Yeah, and also making sure to have it subject-specific, too. So I think it's a good starting point for starting to analyze joint replacements, and I'm sure it can apply to a number of other questions as well.
Yeah, I'm sure. And I feel like there's so many times I do rock climbing sometimes, and I'll just be feeling like I can't finish a route, but then I just see someone do it, and I'm like, they're doing exactly what I was just trying to do, but seeing them do it makes me be like, oh, maybe I can do it, and then I go do it.
Yeah.
So it's like, if someone does this, like, everyone I feel like is always like, oh, it's too hard to combine these two things, but now that someone's done it, maybe we can, everyone
Yeah,
can use it,
definitely.
you know?
And I think it's important too, as both of the models improve, like the musculoskeletal models are continuing to improve as well. And they said some of the limitations are the constraints in the models. As those improve, then the whole workflow will improve too. I thought it was a cool reminder too. The first total knee replacement surgery was performed 50 years ago in 1968.
Whoa.
And I didn't realize that.
Whoa.
I guess I felt like they had been happening for longer than that.
Yeah.
For some reason.
We did that before we went to the moon. Yeah,
Does that seem like a long time to you, or not?
I don't really
time?
know. I mean, sometimes I feel like I have less of a idea for like surgical interventions and things like that. But like, I guess even like cardiac bypass surgery and stuff we haven't been doing for that long, so maybe I shouldn't be that surprised, or I should be surprised. I don't know.
Who can be sure?
I don't know
But
these days.
basically, still up to 20% of total knee replacement patients are really unsatisfied with the surgical outcome, and still about 6% require revision surgery. So there's a lot to improve on still, and because a lot of patients have total knee replacements, and I think it's probably only going to continue to increase. Yeah, and so there's a lot that goes into it, and so even once we have the optimal placement or type of knee replacement, and still additionally designing equipment that can then like implement these observations that we're finding. So there's a lot of different areas to improve on. All right. Now we're going to hop into our interview.
Let's hop in. Let's dive in. Head fast. Here we go. 1, 2, 3. Geronimo.
Ow!
Oh no! Are you all right?
I dove in head first into the microphone.
You dove head first. Hey everybody, we're here today on Boom with Assistant Professor Jacque Cole, who is in the Joint Department of Biomedical Engineering at UNC, University of North Carolina, Chapel Hill, and NC State, North Carolina State.
Hi Jacque, thanks for talking with us today.
Hi, thank you for inviting me. I'm glad to be here.
Could you describe what your lab does? You run the orthopedic mechanobiology lab?
Sure, yeah. So the overall goal of our lab is we really want to understand why we lose bone and why we fracture with a lot of different clinical conditions. And some of the ones we look at are aging, stroke, obesity, and this nerve injury that happens at birth. And so to do these things, we look at kind of 3 primary areas. So we look at bone mechanics. So we look at the how strong bones are. We look at the microstructure of bone and their material properties, just the overall mechanics. One thing that kind of sets us apart from other bone labs is we look at the vasculature within bone, the osteovasculature, which is really crucial for bone health. And then we also look at the metabolism of the bone cells and how they interact with other cell types. The long-term goals, what we want to do is use this information to develop new treatments that restore the function of the musculoskeletal system. It's kind of an area that we call regenerative rehabilitation. It's kind of in a nutshell what we do.
You said that you study the osteovascular environment, which it's the bone and then the vessels around it. I'm guessing the ones that are carrying blood to the bone. Why study the osteovascular environment? Why is this important?
We know that, like all tissues and all cells, bone really depends on the blood supply. And so we know that if we don't have a healthy blood supply, and this is both within the bone, so kind of there's the hard, dense bone called cortical bone. There's vasculature within that bone, and also within the marrow cavity where the cancellous bone is. So all of that osteovasculature, we know that that is essential for providing nutrients and carrying away waste products to the tissue. But we know that bone will not heal properly. So if you fracture a bone, that disrupts the vasculature. The first thing that ever happens in the healing of a fracture is you get invasion of vasculature into that space to kind of help jumpstart that healing process. So bone won't even heal without proper vascular supply, and it won't form initially in utero and even postnatally if you don't have a good vascular supply.
Wow. So you talked about fracture and how this system is important. What are some of the diseases that affect this osteovascular system?
We know with aging, so we get a declining in vasculature. So within the bone, the direction of blood flow can actually change. We certainly get a decline in the amount of vasculature that's there, but also in its function because the flow will change. Of course, with stroke patients, we know it's a disruption of the vasculature in the brain. But we've also seen in humans that you have disruption to the arterial stiffness within the forearm. And so that kind of jump-started our studies, which we mostly do animal models, because a lot of the measurements we do can't be done yet in humans. At least no one has volunteered to give me their bones yet to make these types of measurements. So we use a lot of animal models to kind of build this basic understanding, and with the hope that we'll eventually translate that to humans. But so we know that we see these changes in humans with aging, with stroke, and we're discovering in animal models with the obesity and nerve injury as well.
While we're talking about animal models and how you use them, how well do you pose these or animal studies can translate to human health? Like, you're hoping that concepts will apply, but how have you been able to investigate that or see that in your work?
So we have not yet made the jump to humans. So some of the work we do with understanding this effect of the osteovasculature on the bone is a little ways out. We're kind of at the basic science understanding phase. But certainly these models that we use are well-established models. So there have been a lot of study characterizing, for example, the stroke model and the nerve injury model to show that it really mimics, at least at the musculoskeletal level, the changes that we're seeing in humans. So the hope is that the underlying biology is similar. And so that's what we're exploring and looking at to try to understand the mechanisms for why we see those musculoskeletal changes, to the hope that will help us develop better therapies.
Okay, awesome. And what kind of therapies do you expect to be developed? How do you improve the osteovascular environment? Is it just to get more blood flow to the bones, or?
I kind of envision that it could be a couple of different things. And these are the two avenues that we're studying, is either some sort of exercise protocol. So we know that cardiovascular exercise stimulates vasculature in general. We're still figuring out how exactly that impacts the osteovasculature, but we think that there might be ways to implement either kind of physical therapy type treatments or cardiovascular type treatments to help with that. And the other one is pharmacological agents. So we know some about the pathways that some different proteins that kind of impact that the vascular system in general, and especially within bone, and how the vascular cells in the bone, the endothelial cells and the bone cells interact. We're just starting to look at some transgenic models to help probe that. But I think once we develop some of that basic understanding, developing pharmacologic agents would definitely be in the realm of possibility, because that's been done in other clinical type conditions that our lab hasn't studied, but others have. For example, with osteoporosis, there have been people developing pharmacological treatments based on animal studies using similar techniques to what we use.
Right. And I guess it's important, too, to just understand what's happening biologically to have some assessment of how these pharmacological agents are affecting the system as well.
Right, exactly.
One study we saw, you looked at the progression of metabolic disease and diet-induced obesity on the osteovascular environment, and found that individuals with obesity and metabolic disease experience increased limb fracture rates, even though they might have had a greater bone mass than healthy individuals. And I was wondering if you could talk a little bit more about that study and if you found anything surprising in the study.
Yeah, I think it's pretty well known that people with obesity can develop fractures in spite of having increased body mass or other things that are thought to generally be protective. And the size of their bone can even be larger, which is considered to be mechanically protective against fracture. But there are a number of things that contribute to whether or not a bone will fracture. So you certainly have the bone density, so how much bone you have, the structural organization of that bone, so how the overall geometry as well as architecture of that cancellous bone within the ends of your long bones and in your vertebrae. And then there's the material properties. And so that's where I really think that a lot of the changes are happening at kind of the material level. And it's kind of a nebulous term that people have thrown into a bucket called bone quality. So they say that the bone quality is not good, but what's really meant by that is not really well defined. So our lab looks at a lot of different material properties, such as how perfect the mineral crystals are within the bone, or how the collagen, the maturity of the collagen, and other factors related to the organic matrix. So those different measures related to the material can change. But one of the most interesting things we found in this study that changed is we found actually we had expected the blood flow within the bone would decrease because we think of declined blood flow as being bad. But what we're actually seeing is an increase in the blood flow. So that was really surprising to us. But what we started seeing is that even though you have increased blood flow, it doesn't really tell you how functional the vasculature may be. And so we're starting to look at some of those functional measures now. We're using kind of nano-computed tomography with a contrast enhancement to look at the vascular structure within that area. And so we're seeing kind of, even though there's an increase in flow, the actual overall amount of vasculature that's there is decreased. It's kind of a complex thing going on, and we're still trying to understand exactly what's happening, but it's fun when you get those findings that you don't quite expect, because I think it then opens up new and more interesting questions that help you kind of really probe what's going on.
Yeah, that's really cool. I also do some work with a lot of clinicians, and we always have this problem of terminology and definitions of things. You say bone quality is like sort of an ambiguous or vague, not necessarily quantitatively defined term, but you guys are working hard to look at a lot of mechanical properties, and I think that's cool in order to better characterize and more quantitatively characterize the quality of bones. And I was just wondering, what kind of tool do you wish you had or would you want to have to be able to like test these properties in humans? Or today with the tools you have that you're using on mice, if I wanted to know my bone quality based on your mechanical properties, what would you have to do to my forearm or something? What does that look like, just as someone that's completely naive?
Yeah, so one big one is Raman, that actually could be translatable as Raman spectroscopy. That is a technique that gives you a snapshot of what so bone is composite material made up of this organic matrix that's mostly collagen type 1, and it's embedded with the inorganic mineral crystals, right? So you have both this mineral phase and this collagen phase, and Raman spectroscopy is one of the techniques where you can probe the underlying composition of those different aspects of the bone material. But mostly you have to have like a little chunk of bone that you put under this microscope and use a spectrometer then to get those types of measurements. But so actually one of the postdocs I did at the University of Michigan in the Department of Chemistry working with Mike Morris is his lab has been and there are other labs working on this too, have been developing ways to do that in humans. So coupling a Raman probe with an arthroscope. So maybe you could go inside a joint or near a bone to do that minimally invasively in humans. You can tweak your optics. So with Raman, you have an illumination laser, and then you have collection optics. And if you spatially offset those two things, you can probe deeper into the tissue. So his lab has also done some work on developing those spatially offset probes to do those measurements transcutaneously. So if you had like a superficial bone, like the forearm, which does fracture a lot in humans, maybe you could get that type of answer non-invasively. I think we're a ways off on translating that to humans, but that's certainly they've done prototypes of that and tested it in dog bone and mouse bone. I did work on that some while I was there. It was really some really cool work.
And sorry, just one more question along this line. I'm really interested. I'm always thinking about like, what can we do for humans, which I know you guys are too. I'm trying to think of a way to explain this that doesn't involve going deep into things, but basically we ended up having to do some of our research in the operating room because that was a chance to get access to the brain while, the skull was open. So Do you guys, or is there research currently going on, or would you think about collaborating with operating rooms and things like that to when you have access?
We haven't done any of this yet, but certainly it's a possibility where if people are going in for a hip replacement or knee replacement, because they're opening up the joint and exposing the bone and sometimes even taking some bone out, right? Or in cases with diabetes where they go in to debride bone, you could get some of the damaged bone to study. So yeah, certainly there are opportunities there for those types of scenarios where you could get a look in vivo at, to harvest some tissues to look at. I know another area where people often will gather bone from humans is iliac crest biopsies are actually pretty common, especially in like osteoporosis type studies. So There have been people doing multi-site, multi-center studies where they take these bone biopsies from your pelvis, your iliac crest of your pelvis, and then looking at them with these different analytical techniques, so like Raman spectroscopy, like different CT imaging, like microcomputed tomography, micro CT, and other ways to measure bone structure and bone material properties to see how that looks. There are certainly those types of opportunities for getting bone samples in humans. I haven't figured out a way to do it for stroke patients yet, which is one of the big ones I'm really interested in studying.
Right, because they don't typically undergo surgery like that.
Right. So one of the things we're doing with them, we're starting a new collaboration with it's actually a physical therapy professor at UNC. He treats stroke patients and he does research on stroke. And so we're trying to figure out, are there biomarkers in the blood that might be indicative of early changes in bone so that we can at least identify people who we might need to watch out for or treat or kind of be more proactive in trying to treat so that they treat their bone loss before it happens so they don't experience those fractures. So we are doing some things like that to try to at least identify people at risk to humans. So that's a more non-invasive way, but it doesn't get at the bone structure directly, but it's kind of a first cut on how to look at that.
So we wanted to discuss what it's like starting a lab and also being a new professor. And so we were wondering what your experience has been so far.
So I feel like starting a lab is a bit like being taken out of the kiddie pool and thrown into the deep end without your floaties on. As a grad student, as postdoc, I got a lot of training, and I think this is not uncommon. You get a lot of training and experience with doing research, right? Like we can design experiments, we can come up with protocols, we can measure things, analyze data, we can write. We may probably even get some experience with mentoring undergraduate students or those things, but no one really tells you how to manage a lab. You don't really get that training. There's no class. Well, maybe there are some places, but certainly the places I was, there wasn't a class for that, or there wasn't training on that. And that can be really tricky. Like, how do you select good personnel? How do you talk to people when their work isn't working out, so like they're not doing their job well, right? Or even if you have to fire somebody, how do you do that? And how do you deal with failure, right? So I feel like you have to deal with some amount of failure as a grad student and a postdoc if you get a paper rejected or a abstract for a conference rejected. But I think it just gets compounded more and more as a professor. So now you have grant proposals and papers and experiments, and you have to deal with a lot of failure and getting comfortable with that and making that so that it's not something negative so that you don't feel bad about yourself all the time. I mean, that takes some time. It really took me a couple years to get my feet under me and get my lab kind of running how I wanted, because you don't get training for that.
Right. Do you feel like there is concrete advice that you can give for learning how to deal with failure or some of these other things that you mentioned? Or is it more just you have to experience it to really understand and know how to deal with it? Because we talk a lot we've talked to professors before who have said, I got this advice, but then I didn't really appreciate it until after everything had already happened. And looking back on it, I realized what great advice that had been.
Dealing with failure, I think some of it is just your mindset. So I think this is certainly something that you can start to do earlier in your career, but failure is not really failure. Now I kind of see failure as an opportunity to make my stuff better, right? So not always, but usually if you get a rejected paper or you get a rejected proposal, hopefully you get some feedback as to why it wasn't good, right? Or at least you can talk to people to get their opinion about why they think it didn't get accepted. So I kind of just had to rephrase my thinking to not see it as a failure, but more as a way to figure out a way to frame it better or figure out a way to tweak my questions so that it was more meaningful or even more interesting. Because I feel like in most of the time when I do that and I turn things around, it's better than it was when I first started, right? So also as a young professor, I was hesitant about asking for people's feedback on things and and I had some great mentors and I know they would have been happy to do that, but I was too hesitant to ask for that, to say, hey, I've written this proposal, can I get your opinion on it? Learning how to do that and really asking for that advice and feedback from a lot of different people really makes my work better. And it has helped so much. So I wish I had done that sooner, is to not be timid about worrying about my ideas might not be good enough or worrying about giving people things that aren't completely polished, to get feedback early and often from a lot of different people. For just getting the lab up and going. So my first year was really challenging. First of all, I would advise anybody to try to build in a little bit of a break between either grad student faculty or postdoc and faculty, whichever it may be.
I think I build in a break like every semester or every quarter.
Yeah. Because I feel like I kind of went straight from my PhD into my postdoc and straight from my postdoc into my faculty position. And in some cases, I was still trying to finish things up from the previous thing before I started. So I felt like I was always starting off slowly, or it took time to get going because I was still, and I think that's common, right? You're still trying to wrap up what you were doing before. I wish I'd had a more strategic plan for specific grant proposals to kind of, or other things to help me kind of hit the ground running. Because I've seen colleagues who did that. I think they were better prepared when they started their first year and they were able to really hit the ground running. And I feel like I floundered a little bit at the beginning.
We really appreciate you sharing that experience with people. And I think at any level, what you said about failure is really hard. And have you heard of the marshmallow challenge?
No.
It's this challenge where you try to get a marshmallow to the highest vertical height off of a table with just, I think you've got 6 feet of Scotch tape and a package of spaghetti.
Uh-huh.
I think you might also have a piece of string, like 12-inch piece of string. And they give people 5 minutes. They've done this with lots of different groups like business people, CEOs, grad students, engineers, kindergartners. And actually, the group that wins are kindergartners because they fail fast. They figure out what works and they just get their marshmallow like maybe just a spaghetti length off the ground to start, and then they figure out how that works. Whereas engineers and other people tend to try to construct one elaborate piece and make it perfect, and then they put the marshmallow on top at the very end in the last minute, and it ends up, the whole thing collapses. Whereas the kindergartners, they learn to fail fast and test out their unpolished work. So I think, and I can relate to that experience that you were talking about. I feel like as a grad student starting out, there were all these awesome people around to help in our lab, but I was definitely timid about approaching them because you feel like you're inadequate, or you're just going to bother them with a silly question or something, and you want to get all your information down first before you before you ask something.
Right. And I think it's too, I think there's also a gender gap in those feelings. So I feel, from my own experience in seeing students, I feel like, and this is generalizing, so it's certainly not true of everybody, but I feel like that women are often more timid about sharing unfinished ideas, or maybe things they feel aren't complete or are ready, for people to look at. So I feel like that's something that women tend to do a little bit more than men.
Have you tried to create a certain culture in your lab? And if so, like, what is that culture to you, and how do you continue to cultivate this in your lab?
I try to build a very collaborative culture. So I don't like hierarchical structures. Like, I don't want my students and the other people in my lab to, like my lab manager, I don't want them to see as like me on top and I'm kind of coming up with all the ideas and they're just kind of executing. Because first of all, I feel like they often come up with better ideas than I could ever come up with to begin with. And I feel like if you don't have ownership over what you're doing and you feel some sense of independence on that, then it's not as fun, it's not as exciting, and it's just, you don't have your best work, right? So I try to build a kind of an environment where everyone feels like they have ownership over what they're doing. And then I try to encourage them to be collaborative. So we're big on undergraduate research in our lab. So I try to pair each of my grad students with 1, 2, 3 undergrads, depending on their own comfort level and mentoring and that sort of thing, to get them help so that they can do the things they want to do. And also just to help build that kind of collaborative environment. We do a lot of outreach in my lab, so I find engaging with the community really important, and that is part of our lab culture, this teaching, mentoring, collaborative environment. I try to foster that by the way we structure our lab meetings, so encouraging feedback, encouraging questions.
Yeah, I think that's an awesome structure to have, and it's always good to not feel like things are too hierarchical, but also being able to have like solid leadership, I think, is important. And it sounds like you've managed to do both of those things, which is a really awesome balance. We get to rotate through a lot of different labs to our first year, and I've seen all the different structures in those. Always interesting how people tend to run them, but I think that note of having something that's independent that you feel you have ownership over, and you're a little bit independent of other people, but at the same time having a united goal, I think is also really important. So that's amazing that you do that. And then blending outreach into all of that, just from looking through your lab website, it looks like you guys are really active in outreach, and I think that's awesome. And how do you find like translating your research to the community? Like, do you find that's difficult? Do you find people are receptive, or like if that's helped with your own motivations and things like that? Or has that shaped how you change your research directions? Just really any experience there.
If I could add to that question too, there was kind of already a lot of questions.
Yeah, sorry.
But I saw that you guys played a role in National Biomechanics Day, and I was curious as to what your setup for that was and your involvement in National Biomechanics Day.
That is a lot of questions. So you may have to remind me if I miss one. But in terms, I feel like the community is so receptive. They want to know what we're working on or what cool things we're doing, what techniques are new and what technologies are available. We live here in what we call the Research Triangle. So that's like Raleigh, Durham, and Chapel Hill, because we have several big universities here, including Duke University, of course, University of North Carolina State University, where I work. So because of that, and we have this Research Triangle Park that has a lot of industry that is kind of spin-off companies and other things related to different research going on at the universities. The interest and opportunities for STEM in general are huge. And so a lot of the schools in the area, from the elementary, middle, and high school, a lot of the science teachers, they're just looking for things for their students to do and come learn about. And they love coming to the university because the students love just coming and seeing what the campus is like, right? They're just curious, and they like talking to the students who are here to like, what are their experiences like? They're just really excited to learn about that. And then just seeing what we're doing. Like, what kind of things do you do at a university? What is research? What is biomechanics? And most of them have never even heard the term, right? Because you don't really get that term until college. The community has been very receptive for that. I find that participating in these things really it renews my excitement and interest. Because, I mean, if you see their interest and kind of their enthusiasm over what you're doing, that's exciting, right? It's like, oh, they think it's really cool. It reminds you of how even some of the simple things can be really cool.
Their excitement definitely propagates into your excitement for the research.
Yeah. So when writing research grants, you're often writing, or research proposals, you're writing to a scientific audience, but often a general one. And so learning how to talk about your research at a basic level so people can understand, people from a variety of backgrounds, it makes you better. It makes you better at talking about your work. It makes you a better scientist because it makes you step back and look at things from even a basic level, right? So I think that in that way, working with the community and people in the community, that enriches our research because of that, because it helps my students learn how to do that also. Because I certainly participate in these outreach events, but I really encourage my students to be the leaders and drivers of it. So we do participate in a number of activities. One of them called SCIREN, SCIREN. So it's a network. It's a scientific research and educators network in the Triangle here. And we create lesson plans. And you can create it for any age group in K through 12. We create lesson plans on bone mechanics and other things, and we load them on the website so that local teachers, they can download and use things in their classroom. So it helps enrich kind of day-to-day education that way. So we participate in that. And then the other big one you talked about was National Biomechanics Day, and we love participating in that. So we've done that this last year. We've done it every year since it started, so for 3 years now. So we've always invited a few of our local high schools to come and do that. And in the first 2 years, we kind of I set up different labs in our department and just had them do demos that were on the level of a high schooler, but would kind of showcase something that their lab was doing. But this past year, we really did something different because we brainstormed a lot. So my lab manager, Stephanie Teeter, who really helped organize it this year. So she and I tried to figure out, like, how could we reach more kids? Like, how could we invite more kids because when you do those lab tours, you just can't, there's a limit to the number of people you could invite. So this year we made it more like an expo. So it was kind of based on, I don't know if you guys attended the American Society of Biomechanics meeting when it was in Raleigh. So they had like an expo there. And so it really we liked that format. So that's the way we set it up this year. So we had a bunch of labs, different research labs who participated, but encouraged them to kind of set up these expo type demos, and we did them all in the library and out on the quad or the oval, we call it. The students could come and go as they wanted to. They could rotate to whichever demo they wanted. They could go to the same one 10 times if they wanted. So it just kind of allowed them more freedom to explore on their own, which I thought was really good.
Yeah, that's a really good setup. We've been trying to think of the same thing because similarly, we had the kids rotate from lab to lab, and just walking, like our labs are almost like a mile apart. It's a pretty far walk-in, so that takes up a lot of time. And yeah, it's very limited by the number of students. So I really like the idea of turning it into more of an expo, and then the students can kind of pick and choose which ones they want to go to.
Yeah. And it also challenges, because I had to challenge some of our research groups here to kind of not just do their normal spiel about the research, to really come up with like a more basic type demonstration for something that to help the students understand. So, for example, my lab, we don't really work with motion capturing or force plates, but we set up a force plate and had the students jump and see how high they could jump and how that would correlate with their hang time, and could they get something on the order of what Michael Jordan can do, so trying to relate very basic concepts to them, and they really enjoyed that, more interactive.
Yeah, that's really great. What are you most excited about in the future of biomechanics?
I really think future is better understanding the interface between kind of different tissues. So a couple of the cool things that I'm excited about is the advancement imaging. So we were talking earlier about things you could translate to humans. So one of those things is imaging. So MRI imaging has had a lot of advancements where you can do like micro MRI imaging. MRI is not the best for bone, but it is for soft tissue, so things like muscle and other things. But there's the nano computed tomography. A lot of that technology micro and nano computed tomography is becoming where you can take in vivo measurements in animals. And so if we keep, I think that envelope's being pushed, then maybe eventually we'll be able to do that in humans, to get micro scale measurements in humans. The thing I've seen most recently that is really exciting to me is there's a new field, I don't know if you've heard of it, called mechanomics. You have the mechanics side that's like combining mechanical models, and that would include like structure and biological factors like growth rates of tissues. But also there are a lot of new cool things in omics technology. So you've probably heard of like genomics, proteomics, metabolomics, so those omics things. So those can now be done at the single cell level. And so I think combining those mechanobiological models with that omics, this new field called mechanomics, trying to probe these complex interactions between cells and even multiple cell types like bone and muscle and their different microenvironments. So I think that advancements in that area could be huge for advancing biomechanics, especially things like implant design or prosthetic design, where that interface with the tissues is so important. I'm more on the tissue, cellular, molecular side, so I find that to be exciting in the future of biomechanics.
Yeah, that's so awesome. I would never even think about that as being something that we're on the forefront of, and that's why I love these interviews, because I feel like I learned so much. It seems like science is starting to converge on this. We've been studying things in isolation in the past, and now we're finally starting to be able to connect things together and not just look at one property of a system, but look at it from the perspective of genome, like some omics characteristics and also some mechanical properties, which I think has not really been a thing that's been possible in the past.
Yeah, and a lot of these things are becoming available in humans. Like you can do these omics type things in humans. You can do those type of mechanobiological models in humans. So if we can advance that connection between the two, I think that's going to be really exciting.
Yeah, that's awesome. If you could have a biomechanics or research or science superpower, what would it be?
I really need something to help me keep up with my 4-year-old. So I have a 4-year-old son who is quite active, loving hoses and vacuum cleaners. Has some interesting hobbies. If I could have something to help me keep up with him, that would be really awesome. But no, so seriously, I think my superpower would be something like X-ray vision, but maybe like CT vision or nano CT vision, so that I can see inside people's bones to help diagnose the problems in their structure or in their vasculature. That would be really cool.
That'd be so cool. You'd be wanted by every clinic in the world.
We talked about failure and how to embrace it. I was wondering if you have any maybe fun research fails that you would be willing to share with us.
Yeah, so when I was a graduate student at Cornell, in Marilyn Vandermeulen's lab, so she does a lot of mechanical testing. So I was studying osteoporosis, and so I was doing experiments on cadaver spine bone. So I had these cores of bones that were embedded in like these brass end caps that would grip to compress so I could get the mechanical properties. And so I was trying to like apply the precondition and then compression. And I kept trying it over and over and over in practice samples. And every time it would like precondition and then it would pull apart. So it was not compressing. It was pulling completely apart, destroying the sample. And so I kept trying like over and over. I checked all of the parameters and everything. I tried the feedback controller. And it turned out to be like some simple setting on like the X tensometer, which measures the displacement that I was using. It was just like some interference. I'm not even sure how I fixed it, to tell you the truth. I think I just tried like 10 different things and eventually something worked. And so that was my biggest fail though, and that took like 2 months to figure out. It was so frustrating. And I think that was another thing where I was doing it all on my own. I wasn't asking questions because I was kind of embarrassed that I couldn't figure it out. Yeah, that was my big fail.
Doing the opposite of what you want.
Yeah, exactly. It's like, this is not working and it's not helpful. I did have another one. So when I'll give you two.
Wow, 2 for 1.
So when I was a postdoc at Michigan, I did put 2 postdocs at Michigan. So the second one was in orthopedic surgery. And when I was doing that one, I'm a mechanical engineer, right? I had done like mechanical testing and I'd done finite element modeling. And so this postdoc was on cell culture. So I was learning about bone biology. So I really had no idea what I was doing at the beginning with that. I remember I had a pretty big experiment going and I had a lot of plates with a lot of cells. And so this is probably a lesson in like study design also. I think I had bitten off more than I could chew. So each of my time points was like a 24-hour assessment. So it would take me 24 hours to do everything I needed at the time point. It was really ridiculous. Anyway, so I had the cells, and you add trypsin, which is this chemical causes the cells to lift off the plate, and then you can centrifuge them down into a little pellet, and then you can resuspend them in media to get the volume that you want, right? To get the density that you want, to put them on a new plate. So I had put them in the centrifuge to get them down. I had my nice little pellet, at which point I was supposed to aspirate off the extra media and then resuspend in a known volume. Well, I aspirated my cells. So, yes. So that was super, super frustrating. Lesson learned, do not do things when you're really, really tired. And study design, don't set up experiments that take you 24 hours to do so that you're really tired when you do them. That only happened once. And then I was so paranoid that was going to happen again, and never happened again.
Oh, that's good.
Yeah, once you make a mistake like that, you tend to remember.
Yeah.
That's a good lesson in study design. I think sometimes we get so caught up in the science, or I'll speak for myself. I'll say I get so caught up in the science that I forget that it'll be a human doing this analysis or experiment.
Yeah, exactly.
And I should probably make it work with how I want to do it.
Yeah, there are limits to what we can do.
Well, thank you so much for those awesome fails and for being open about sharing them and having such awesome perspectives on all of the different questions we've asked so far.
Yeah, I learned a lot about osteovasculature, which I hadn't learned about before, and then learning about some new fields. It was really exciting, so we really appreciate you taking the time to do this with us.
Yeah, maybe in some of our musculoskeletal simulations, we should add some vasculature, and that can be a new parameter.
There you go. I would love to collaborate with you on that. That would be awesome.
That would be really cool. I mean, muscles need blood, right?
That's true.
Yeah, exactly.
Well, thanks, Jacque.
Yeah, thank you very much. I really enjoyed it.
So that's a really awesome interview that we just had with Jacque, and so nice of her to share both her awesome research and really amazing insight and perspective into setting up a lab, how to build kind of culture you want, and encourage really independence in research. I think that's really important. And she also talked about some cool technology that I hadn't really heard about. What was it ramen?
Ramen
Spectroscopy?
Oh, yeah. I couldn't remember the second word. Ramen is really sticking, though.
Why was ramen sticking?
Well, I think... So during the interview, she said ramen, and Hannah and I just immediately look at each other and think about ramen noodles. And we are so in sync with this. It's concerning, and I don't know if it's...
It was so insane.
Yeah.
I just gazed into Melissa's eyes, and essentially her eyes said ramen noodles to me.
Yeah, and we communicated ramen noodles to each other. And then later, Hannah informed me of a very interesting news report where allegedly some thieves in Georgia escaped with nearly $100,000 worth of ramen noodles.
Or so the police say.
That's what the police say.
Do you think the police actually just kept them for themselves?
Yeah, if I was the police, I would. You know how many lockers they're going to need to keep all that ramen noodle until they figure it out?
Or how many
Don't
stomachs?
they, like, keep all the Well, apparently they had a 53-foot trailer
Oh my goodness.
that was parked outside of the store to steal all this. Because honestly,
Wait,
I don't
they stole
even
them from
know-
a store?
I think,
So
from
they
a
had
warehouse.
they had to run all these noodles
So many noodles.
out to the truck?
I didn't even know you could fit $100,000 of ramen noodles in one area.
Wow. They're like, 30 cents a package, so it's a lot of noodles.
So many noodles.
So shout out to one of our biggest Boom fans, my mom. I was telling her about this ramen noodle incident because she was informing me of like actual current event news that was happening in the world. And I said the only
And I
news
was like,
story
listen
that I've
up.
read
I am cultured.
24 hours is this one. And I told her, and she goes, her first question, no joke, is, well, did they get the flavor packets too?
Your mom knows what's really
She knows
important.
what's really important in life. These are the things that she has taught me.
That's amazing.
I said, Mom, yeah, it wouldn't be worth it without them.
Yeah,
Wouldn't be
honestly.
worth stealing.
No way. Let's talk about some research fails. Or just fails.
Just fails. All the fails. So
Let's talk about our learning experiences.
Research fails. Yes, it does.
Well, I just wanted to let everyone know that I am okay, despite the fact that for a while I was using these really intensely, these really intense chemical wipes that we use to sanitize a lot of our patient equipment, which is good because, you know, we're sanitizing things.
That's good.
Right. But they kill everything. They kill like HIV virus, HPV. They kill all of these things.
Wowza, that's intense.
And I was using them one day, and my coworker was like, "Oh, like, why aren't you using gloves?" And I was like, "What? What do you mean gloves?" And she was like, "Oh, like, those are really powerful wipes. You should probably wear gloves with them. Actually, you're required to wear gloves with them."
Oh, no.
So, who knows what has been happening to my hands and the rest of me that's touching these wipes. But I'm okay now, and our equipment is very sanitary,
Yeah, and so are your hands.
and so are my hands.
But
so
I'm really glad that no one was injured in the
no researchers were
sanitization
harmed
of your
the
equipment.
process. So that's my fail, because I haven't. Melissa complained last time that I haven't contributed many fails
Yeah,
to this.
Hannah's not failing enough. No, I'm just kidding. She's
No,
awesome.
It's just because I haven't tried.
Well, we both almost failed after our interview with Jacque.
That beautiful interview that you just heard.
Yes. So we were really excited because a Boom friend, Nathan, recommended that we use Zencaster to do the recordings because the quality was higher, and I agree. I think that after listening to it, it sounded a lot better, which was exciting. But we said goodbye, and...
This is a Skype software. It's sort of like an online Skype thing that
Yes.
you and whoever you're Skyping record with, and then you get an audio track for each of you.
Yeah, exactly. And so it's only audio.
It's only
And so we hung up, and then we're waiting for the files to download, but for some reason only the recording of me and Hannah was downloading, so it would be like us asking a question and then like 5 minutes of silence, and then like maybe some giggles, and then another 5 minutes of silence. So we were really concerned, and then Hannah very quickly found out that the person on the other line has to keep their browser open to be able to download their interview. And so, yeah, so we had to quickly look up her phone number, which she has multiple offices, so that was scary. But we were able to contact her and
right away.
Yeah. And she picked up and we were like, oh, hey, Jackie, did you close your browser by chance?
And she was like, no, but I definitely can. I can do that right now.
Yeah. We're like, no. Don't do that, please. Could you open it back up, the web page? And thank goodness, as soon as she opened it back up, it connected her again and then downloaded.
It just appeared out of nowhere. Like, I genuinely thought it was gone forever.
Yeah, and honestly, my biggest fear has always been we ask for, an hour and a half of somebody's time, and then something happens to the recording and it deletes it. I have this fear every time I record for anything, and it's really scary. So I'm just really glad that it didn't happen. And
thank you, Jackie, for being really responsive, answering your phone, and not closing your browser.
Yeah, we really appreciate it. This podcast was brought to you by the International Society of Biomechanics. To become a student member of the International Society of Biomechanics or a regular member of the International Society of Biomechanics, who are just as important, you can go to isbweb.org and register as a member, and this will get you discounted rates for the 2019 combined ISB and American Society of Biomechanics conference in Calgary next year.
Woo woo.
Yeah, as well as a student, you'll have special opportunities through ISB for student grants, which will be due in mid-December is the next call. So now would be a good time to sign up as a student member. And also follow ISB on Twitter at ISBiomechanics, and you can like our Facebook page, the International Society of Biomechanics. Why don't we have an International Society of Biomechanics app? Ooh, okay. If anyone thinks
wants to make an app
for ISB,
we will give you 5 whole boom stickers.
Yeah, maybe even 6. But I really like the Journal of Biomechanics app because you can just go on and see like the articles from the current issue release, but then also the most read. So you can see kind of what ones are trending now. Yes, get it. In the morning,
do you have to be a member to
instead
have
of checking Instagram, you can check the International Society of Biomechanics app.
What's this?
I mean, not International Society of Biomechanics, Journal of Biomechanics. These are separate things.
How do I get it?
And I'm not trying to promote this app, but it could actually be really awesome to have an ISB app.
You could have Boom as part of the app.
And because Biomechanics, which is just this really awesome website from ISB, which talks about people post their questions about biomechanics, and they post job opportunities, like even like postdocs and grad students. And so it's a really awesome resource that ISB started, and that would also be really cool to incorporate as an app, just so it's a lot more easily accessible. And it also posts about conferences and grants and really useful things. So we could have like what's trending in biomechanics too, and then like pull up like biomechanics Twitter. Man, I'm getting really excited about this.
There could be like a whole fail section.
Oh, that
where
sounds
people
amazing.
could like post their fail.
And a boom section.
And a boom section.
Okay.
And there could be a button that's just like boom, and people can like just boom from anywhere at any time.
Yeah.
Boom. Boom.
We'll be booming all over the world.
And there'll be like a map of where people are booming.
I love that.
And it'll just have a little boom, 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 boom.
You can't see what was happening, but Hannah was just pointing booms all over the recording studio. Okay, everyone. Next project is an ISB app. So
ISB app.
Contact us.
You hear that, future student rep?
Yeah, so please contact us at isb.studentrepresentative@gmail.com if you would like to contribute to the podcast, or we can get started up on some app development as well. So thanks for listening. Biomechanics off our minds.